Okay everyone, so in this video we'll understand image generation using PixelRNN and PixelCNN. Well, the main aim of this entire presentation will be to understand PixelCNN, but I find it useful that you understand PixelRNN first because as we'll see, PixelRNN is a natural precursor to PixelCNN, and that is also what happens when we look at these papers. So our main aim is to understand PixelCNN, but first of all we'll understand PixelRNN, pixel recurrent neural networks. Both of these papers are via Google DeepMind, and they are in the domain of image generation, not via GANs or not via variational autoencoders. And after PixelRNN, after a few years, I guess, they published Pixel, no, not a few years, but whatever, they published PixelCNN, which we'll see is a better version of PixelRNN, so to speak. Okay, so let's go. So the agenda is PixelRNN. We'll understand architecture. We'll understand what these row LSTM, diagonal by LSTM means, which are, I guess, the main contributions of this paper. And then we'll understand PixelCNN. We'll understand what a blind spot problem is. We'll solve for the blind spot problem. And then we'll do a big gated PixelCNN and we'll see the results. This is just something that we'll understand as we go. So image generation models. And what I claim is, and my statement will be that unsupervised learning is the way to go for image generation models. And we want to model distributions of natural images. Somehow a model should learn what nature, what images can occur in nature, and the rules that allow an image to be real, and what are the rules that that deem an image to be fake. Some sort of that distribution we have to learn. And we need a model that is expressive, tractable, and scalable because image generation as a problem is a vast problem, and we need something that scales and expressive. So auto-regressive models, what this entire thing means from this, and just by focusing on the right hand side of the image, you will be able to understand what this means. That is, if I have an n square, that is a image of n square pixels, and I have pixels till one before this xi. What this entire equation on the left means that we have a pixel xi given x1, x2, x3, x4 up to xi minus 1 and find the probability of that pixel. Basically just dumbing this equation down, all this means is output a pixel one by one, scanning an image from left to right, output a pixel one by one given all those pixels that came before it. Okay, that's simple. But what do we do in case of a color image? In case of a color image, the thing is exactly the same. It's just that we give an arbitrary order between R, G, and B channels. So in this image, if you can see, all the blue pixels are ones which we have till now. When we are calculating the probability for pixel R, we take all of these pixels. When we are calculating the probability for G, we take all of these pixels and also the pixel which we just generated, which was for R. And similarly, when we do it for blue, we take R and G's recently generated pixels as well. So that's what this equation also means. Sorry, this equation. P of I give I in R channel is for x less than I. P of I in G channel is all less than I and I of R. P of I xi in B channel is all of x pixels less than I and R and G. So what is this model's input output? What this model as a black box looks as a black box. So all of these models take the image of size n cross 3, an image, and output tensor size n cross 3 and 256 that corresponds to all the probabilities of that particular uh, color number, basically from 0 to 255, and we have a probability distribution. We have a probability distribution for all these color values, so to speak. Okay, so architecture in the paper, what is this? So we have an image n cross 3. We do a convolution 7 cross 7 image convolution. We do some some blocks Well, in RNN case, it will be an RNN, but in CNN, pixel CNN case, this will be something other than an RNN, something which is related to CNN. And we'll do a convolution and then a softmax, and then we'll have an image which will give us probability values for all 256 numbers, and n cross n cross 3. That's it. So now let's get into it. Let us go into pixels RNN now. So these are the LSTM equations. These are very complicated equations if you're seeing it for the first time, but I encourage you to understand this from a meta perspective, from a higher perspective. What LSTM equations are these. They Each LSTM has states and each LSTM has gates. What are the states? States are basically the state of that equation and what state of that LSTM cell, that LSTM thing. And what the gates are, gates control information flow on this particular time step. That means from this state to the next state in time, what information will flow, that is controlled by gates. And gates and states, all of these both of these two units in an LSTM cell are intertwined by these equations. So for example, xt is our input for an LSTM, and st minus 1 is a state of t minus 1 time point. So at each time point there will be an xt input and st minus 1. We have this learnable parameter u and w. So we have this I gate, which is sigmoid of xt ui plus st minus 1. So a previous state times something and the current inputs times something. Similarly, we have the f gate, which is also calculated in the same way. We have the o, and which is also calculated in a similar way. And we have a g gate also, which is in fact tan h, because tan h takes all values from minus 1 to 1. Basically, sigmoid does not. And we have this CT, and what this CT will give us a way to calculate the next state. Basically, all of this I, F, O, and G and C, all of them come together in equations to give us the S of time point t, and that will be used to calculate S of time t plus 1 and so forth. So CT is CT minus 1, which is previous time point, dot product. This is pointwise dot product with f plus g and pointwise dot product with I, and s will be tan h of ct dot product with o. So we have used all of these equations to give us st. This is just something by design, and I encourage you to go and find some better explanations of LSTM equations. I'm sure this is not enough if you're seeing it for the first time, and this is rather confusing. I admit, for me too, but you can go and find it on YouTube. There are plenty of good resources. Now, what do we do in case of an image thing? All of this LSTM things, they only work for one-dimensional data. That is, let's say words or time series, so to speak. Now, how do we, you know, extend it to images? Well, what we do is, instead of doing matrix multiplication or all of these equations, inside all of these equations, we do convolutions. We do convolutions. So what we have is KSS, that will be a kernel for convolution, time convolved with hi minus 1, and KIS with xi. All of these, what is happening on the right hand side of this curly bracket is all of these four equations are combined into one, and this KSS is a similarly four times bigger matrix, that is four dimension, higher in four dimensions, so to speak. So just forget about this, just forget this entire thing. Just know that whatever was happening in LSTM for matrix multiplication, this entire thing is going to be translated to convolution in our case, and you'll see how this plays out when we go into PixelRNN. Similarly, Ci is Fi and Ci minus 1 plus I of Gi and Ii times Gi, that is pointwise dot product, and Hi equals to Oi and dot tan H of Ci. Don't worry about it. We'll see in images how this entire process looks. So this is the raw LSTM, what the paper is suggesting. So what happens is, we have this first row. Let's say we have this first row, but it is given to us. What happens is, we send this entire first row into a black box and we get the entire second row. And then we send the entire second row into a black box and we get the entire third row. So that's what row LSTM means, that we are going row by row. We are going first row, then second row, and third row. Okay, so how does this work? Well, we give the third row, and when we get the fourth row. But then how does this work is the question. So for each and every pixel in the row which is to be obtained, we look at the pixels above it, we look at the pixels on the top right of it, and we look at the pixels in the top left of it. So this is how it progresses. For the second pixel, this is what the convolution part of things look like, the one we saw in that equation. This is the third, this is the fourth, this is the, and so forth. So this is the now let's look at this equation. So what KIS means is KIS means input to state component. So for example, let's say we have this image, this image of a flower, and we have pixels looking like this. Now what we do is we have convolution that goes from input to state. That is, we take the input image and we go to the state. So there are basically two layers to this. Now we'll get to understand this. KIS means input to state. We have an n cross n cross 3 image that was an input, and KSS means K state to state. So what state to state means, using previous rows, what will be our, you know, input to this particular row. So we'll understand that. So we go to KIS, we have this convolution kernel, we do it with XI. XI is the input, that is this green parallelogram on the image. And by choice here we have only taken 3 as a neighborhood, and we do convolution on these 3 and we go on further. What about state to state? Now in state to state component, as you might have guessed, we use the previous row and do the same convolution there, and now we add these both together and do a sigmoid. That's what this entire equation means. Now, what are the advantages and disadvantages of that? Well, first of all, let's not read into that slide, and I think the advantages will be pretty clear. From what we saw in that particular first slide, which was doing pixel by pixel by pixel, taking all the pixels that was before this and doing probability for n square time points, for n square pixels, basically one after the other. I think one thing that you can clearly conclude that this is faster, this is much faster. If that was big O of n square, this is going to be order n because there are only n rows and we are doing one row at a time. Well, the next question you might ask is it possible that, is it really true that we're doing one row at a time? Well, it is, because all of these individual operations can be parallelized. So all of these n columns can be outputted at once. So all of this entire row can come out as output at once. Okay. So we have completed state to state component. We add them and then look at the advantages. Advantages: compute the state for an entire row at once, so it's much faster. Instead of going pixel by pixel in each row, we are doing n pixels at a time. The disadvantage is that this does not include all information in the image. So this has a triangular receptive field. What that means is, for example, if you look at this particular red pixel in this image, we only have information on what's above it. What are the 3 pixels above it, and for all of these pixels, what are the 3 pixels above it, and so forth. So this moves this entire receptive field, or what information this red pixel is looking at. It moves in a triangle. It moves like a triangle in an image, and it obviously does not take into account all of these pixels, all of these crossed pixels. So that's important information being lost. Now, if you think about it, the pixel which comes in the bottom left corner of an image. So a pixel that comes in the bottom left corner of an image, for that its receptive field will only be the top left half of the image, and that's it, because its receptive field is going like a diagonal on the image from bottom left to top right. I want you to construct this mental image because I'm unable to draw with pen on this PPT for some reason. Never mind. So how do we solve this problem of, having a very stupid, let's say not stupid, triangular receptive field, or something that does not use entire context? Well, the idea is, instead of going row by row, instead of going from top to bottom, what if we go on diagonals? Okay, let's see if it even makes sense. So this is what is happening. First pixel, then the 2 pixels on a diagonal, then the 3 pixels on that particular diagonal, and the 4 pixels, and then so forth. How is this calculated? Okay, for this particular black pixel, what we do is look at the pixel on the top of it and on the left of it, and so forth. For each and every pixel, that's what we do. That's what we are doing. We look at a pixel on top of it and on the left of it. This ensures that we are not looking at any future information. By future, what I mean is no information on what's to the right of black is included in black. Only what's on top and on what's on left, which is basically past, so to speak. And that's how it's computed. It's computed diagonal by diagonal. But then you're going to ask me, whenever we look in this particular, let's say, look at this black pixel, we're only going to include information that's in a rectangle which is on the left of black and on top of black. We're not going to include information that's on this particular row. If you can see my pointer, a row which is on top right, which is not entirely right, but top right of black. So that's also important information. So good question. So we are going to include another LSTM, another diagonal LSTM, but it's going to go in a different direction. That is, it's going to go from the top right and down, and in the same way. So this is what the entire thing looks like, at least for a pixel on the left hand side diagonal. It looks at images on the top and on the left, and as I said, it takes all information in this rectangle into this view, but it does not take these whitened pixels into information. What we do is, in order to, well, the next question that you might ask is, how do we really calculate this thing? What we do is, instead of going diagonal by diagonal, we shift each row into itself, and we do one similarly row LSTM sort of thing, but instead of having a convolutional kernel that's 3 cross 1, we have a convolutional kernel that's 2 cross 1. That is, take only what's on the left and on top of that. So this is like a row LSTM, but it's just column wise. So that way we can have a faster process. Instead of thinking of this in terms of looking at a pixel on top and looking at a pixel on left, what we do is we skew the image and we do a convolution on whatever the column was before it. Similarly for this right hand side diagonal column, when if we were to just go about and do this, that take a pixel on the top and take a pixel on the right, we have this information that is in the future of red, and that is something that we cannot take into consideration. So here's the idea. What if somehow I were to not include this black pixel? That is, if you look into it very carefully, where my pointer is, this image, this where my pointer is, this pixel is already taken into consideration by the previous version of the LSTM, and we don't want this. So what if we just shift the entire thing down by one? What will happen now is, we'll have all of those pixels which were not included previously, and we will have that information. We'll also have some duplicated information, but we don't mind. And we'll do the entire thing and the full skew thing again in the similar way. We take the entire row, shift it on the left one by one, and what we do is do a convolution, but just not on the immediate neighbor. We do on convolution on the pixels which are a bit further in the diagram. So if you look at this, we did convolution on the pixel that was its immediate neighbor, but here, because we don't want this future black pixel to give us any information, we take it one step ahead and skip one immediate neighbor and do convolutions on that. So this is simple. Take an image, skew it on the left hand side, skew it on the right hand side, take convolutions column by column on the left hand side skewed image, and take convolutions column by column on the right hand side skewed image, but just keep in mind that we skip a neighbor. Okay, so now we have a finished state to state component for this particular LSTM. That is, we take this entire discussion which we had, that was for the state to state component. Advantages. What is this advantage? Advantages is it uses it computes the state of an entire diagonal at once. So uh, although not as fast as uh, row LSTM would be, but it's still fast enough because it computes diagonals, entire diagonal at a time. So we take an image and we put it in a black box and bam, 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 we get diagonals after diagonals. It has a global receptive field. That is a major advantage over the row LSTM, and it uses all available context too. So this entire thing now, what we discussed earlier, what this block is, we have in the paper architecture, we have residual connections on this block. This block here will be the diagonal LSTM, bidiagonal LSTM block. So I'd like to add a point here. I'd like to add a note here. All of these blocks can be different on whatever our choice is. For RNN row LSTM, this block will be a row LSTM block. For this bidiagonal LSTM, it will be a bidiagonal LSTM block. And for pixel CNN, as we'll see, this block is pixel CNN block. It's just not something to worry about, but I've just added a point. Now, masked convolution. This is something that is just architecture choice that we are using. Instead of calculating this thing one by one, what they do is that they give a mask to all convolution kernels so that it does not have a input at this. But what this does is mask convolution. If you're not looking at this particular convolution kernel on the bottom image where my pointer is, this will come later. What this actually means is mask convolution is in the same way when we studied that equation for the color channels order, that when we are doing an RGB thing, first have R, then G, then B. First have R, then G, then B. That is, when we are learning things on R, we should have no information on the G and B of that particular time point. Similarly, when we are doing for G, it should only have information on R of the previous time point and the context. So that's what it is. If you look at this middle point, whenever we have R, it only depends on context. When we have G, it depends on context as well as R of that previous value. When we have B, it depends on context, R and G, and similarly and so forth. And mask B is just for the case in input to state component. That's all. That's all. So as you can see, input to state, there is mask B, because in input to state, we are not worried about the previous position. In state to state, we have, sorry, I misspoke. In input to state, we are worried about the mask, and on state to state, there is no mask needed. Just that's not a big deal. We just want to understand what is going on in this entire image. So this is what completed images looks like on Pixel CNN and PixelRNN. So as you can see, given first half of the image, we have its completions and how it looks in comparison to the original image. Okay. So let's go to PixelCNN now. This is the main part of the paper. This is where we will understand, where we learn new things. So why do we even need something other than a bidiagonal LSTM? This is training is much faster than RNN. Why? Because every pixel is independent. That's what PixelCNN claims, that we will treat each and every pixel independent, and that's why it's faster. For larger image, this is a very big advantage. PixelRNNs, however, give better performance. Okay, so let's try to combine the strengths of these both models. That is, have a CNN, have some sort of a convolution neural network, and then have some sort of a recurrence thing also. So that's what they're saying, that as convolutions can be applied to each and every pixel independently, and that's why they're much faster. But RNNs are better because they are using information on everything that's previously present. So what we are trying to do is, for example, let's take a pixel, in this case this blue colored pixel, and convolve with all of the images, all of the neighboring pixels basically previous to this pixel, so to speak. So this blue, this yellow one, this yellow one, this yellow one. If we convolve a pixel with all of these neighboring pixels, we'll have information on these coming into this particular pixel. So that's what mask, when we looked at it in the previous part where it did not make much sense, that's what mask means. Mask A means here. That is when we have a particular kernel. In case of a convolution, this would have been an entire kernel, but no, we cannot have information for pixel number 5, 6, 7, 8, 9 into pixel 5, because these are future values. We only want values for pixel 1, 2, 3, and 4 to give us any information into this current pixel. So that's what mask means. A masked kernel will zero out. This is what a mask will look like on the bottom left of your screen. A mask will zero out all of the values for future and current present time pixel and will only contribute values from a past of pixel 5. Okay, so you can pause and spend a few seconds on this to understand what mask is doing. It's only allowing values of the past to give us any new information about the present. We are not using values of present and future. And in case of a normal convolution, when we do a normal convolution on an image, we are doing this entire thing on an image where we take the values of the future as well as the past as well as the present, because there are our aim is not to generate image. There our aim is to learn things from the image, and that's why we need all the possible values. In this case, our aim is to generate image pixel by pixel, or let's say in the future I give it a half completed image and I wanted to generate what's coming further. So in that case, I do not have any values in the future. It does not make sense to take any values from the future. What we need is only values from the past. So anyway, if I were to do a convolution in such a masked way on this particular pixel blue, what happens is the first layer CNN, it takes all of the values which are given by yellow. Okay, very nice. What about a two-layer CNN? So for each of these values also we go a layer up, and what we see is, as far as the pixels on the left are concerned, all of these values are taken into consideration. But what about the pixel on the top right? For the pixel on the top right, it will only have values up till its top right. And therefore, as you can see, when we go deeper and deeper into this pixel CNN layer, you can see that for this blue pixel, for pixel blue, which is our aim pixel, you will see that there are these particular brown, or sorry, there are these particular pixels which have not contributed to the value, because as you can see, the frontier of the convolution grows diagonally. Instead of it growing diagonally, we want it to have values of everything that's on a row above it and everything which is coming before it in a row. So this is a very key thing that they realized. For every pixel, look at every pixel in an image. It will be in a row. Just look at all of the rows above that row. We want all of those values because they are in the past. And for that pixel, look at all of the values in its row before its column. So we need all those values too. So what this blind spot is, how is this arising? So that's what we are discussing over here. Supposing the 3 cross 3 kernel and postulating, let's say, 2 or 3 layers, looking at this blue pixel, in the first ever layer, we only have these top 3 values, or top 3 and the one on the left. And similarly, going one layer deeper into this, we have for this particular pixel on, we have the top 3 and that, and so the blind spot propagates as we go deeper and deeper into this layer. Now, what is the reason for this blind spot? As you can see, right hand side of this particular slide, on the right hand side, this the absence of this connection in a convolution results in the blind spot propagating, because when we are in this pixel, we are not able to take value of this darker green pixel into the consideration of our model. We only go up till here. For this pixel, we are only considering these 4 values, and similarly and similarly. So because these are absent, these values are absent, the right hand side connection is absent in a convolution kernel, there will be a blind spot and there's nothing we can do about it. So how about make a new filter which still have this direction? I know it's illegal. I know that we are not allowed to have this particular future information into our consideration, but let's do it anyway. Let's see what happens. So this is how a feature map will look. For example, that this black pixel, the first one has all of these, and then the second layer has all of these, and this will propagate further. And as you can see that it will have, when it's going further and further into the image, let's say 15, 20 layers or whatever, you can see that this will have all of the values above this black pixel. On a rectangle above its black pixel, all of these values will be taken into consideration, right? As it goes further and further from this particular type of filter, it has a 2x3 rectangular sort of filter. It will have all of these values above it. So now here comes an idea in my mind. If I have a pixel and I do this sort of convolution on this 2x3 filter sort of convolution on this, and I know that this is illegal because it is taking values that are in the future of its own row. But other than that, it's awesome because it has all of these values above it. If just not if not for this if not for the values in its own row to the right of it, it's just perfect. But as it's illegal, we cannot do it. But what if I were to pass this information to the pixel below me, so to speak? If this black pixel thinks selflessly in its life and it says, well, I have all the information that is in a rectangle above me, but I cannot use it. But I think this will be useful for the pixel which is directly below me in some sense. So what the authors, or what the genius idea here is, calculate this sort of convolutional filter for each and every pixel, which we know is illegal, but then pass this information down to the one pixel below it. And similarly, for the black pixel too, that is highlighted here, it will get some information from the above pixel. So that's what happens. But then you will ask me that for this particular blue pixel, if it's going to receive information from the pixel that's above it, and only this rectangle, it's going to miss out information in its own row. No, that's not an issue. We just add it. That's not a problem, right? So that's what we are going to do for every pixel. For each and every pixel in this image, there are going to be two sorts of convolution filters. One convolution filter will be a convolution filter that acts on a pixel above it, and similarly one convolution filter will act on a pixel in its own row so that it has the values if its own row. So here we see that a feature map can be separated into two parts according to the status of the rows: the rows containing the predicted spot, the rows without the predicted spot. So the rows containing the predicted spot will have this sort of a convolution filter. That is, it only has this, all of the gray areas are masked, and the dark blue is the one we are predicting, and this one is the convolution filter. So as this is just this is basically a row convolution filter, and as we go deeper and deeper into the layers, the entire row information is taken into consideration. And similarly, similarly the one which the rows without the predicted spot, we use this entire rectangle kernel, and pass the information down to the pixel below it. Basically, that's what is happening here. That's what the pixel thought selflessly. And as you can see, this mask contains this particular arrow, this connection. And I would encourage you to spend a few seconds on this slide, because this is when I read about this, it blew my mind. Like, something like this can be done. Okay, so we're going to go further and see how this works. I wanted to upload it in parts, but I guess one part is enough for it. So construct the horizontal and the vertical convolution filters at the same time. So what happens is, for each and every pixel, we have this set of a convolution filter, which we are going to call the vertical stack. Oops, I'm sorry. This sort of convolution filter and this horizontal convolution filter. Now we do with this, we calculate the vertical stack, we do the horizontal, and we calculate the horizontal stack. Now here is where the passing down to the pixel below me comes into play. As you can see, this purple thing is what we get as output from the vertical stack. But because we cannot directly use this purple thing directly, what we are going to do is shift it one below, pad it on the top, and use the dotted one as our actual values. So here's what's going on. First of all, we take that entire thing, we calculate the purple convolution filter, we take out the last row, and we add a zero padding or whatever padding on the top of it. So that's important. That's what is happening. That's what is going to happen when we say that we are passing this information down to the pixel below me. Indirectly, I'm going to shift the entire vertical stack by 1 point, and we are going to do a padding. It can be any sort of padding. And now when we add this is the new feature map for that particular pixel. So for each and every pixel, this is what results. This feature map is what is going to come out. Now, as you can see, by doing this process, there is no blind spot problem. So we have solved the blind spot problem. And for each and every pixel, it has the entire receptive field by doing convolutions and convolutions only. So now we have the CNN thing. Now we want to somehow include the RNN thing into this. Well, why? Well, why would you ever want to care for RNN? So a potential advantage is that pixel RNNs contain multiplicative units in the form of LSTM gates, which may help it to model more complex interactions. So multiplications and nonlinear activation functions. So this will allow it to approximate a function in any form possible, right? That's what neural networks want to do. They want to model nature. They want to model images in nature, but that's not possible if we will only have linear things. We want some sort of non-linearity so that it can approximate a function. To amend this, replace the rectified linear units between the masked convolutions in the original pixel CNN with the following gated convolution unit. Okay. Rectified linear units between the masked convolutions in the original pixel CNN with the following gated activation unit. Okay, what does this mean? I'm sorry, my laptop. Okay, so I'm sorry about that break, about that cut in the video. We'll get back to it. So, why we are doing gating? We are trying to do gating because of the proposed benefit that we get from gating. That is, we have a better modeling on all sort of natural distributions which can occur in nature, so to speak. So, for example, what we are trying to do here is if we have an X image, we have a gate which is G gate, like what we had in LSTM, and we have a F gate. We are doing convolutions in that particular thing, and we are going to do an element wise more multiplication. So to get Y. So take it one step further. Just be with me here. They're going to do abstract things now. Given a high-level image description represented as a latent vector H, okay, something about an image in a vector H, we seek to model the conditional distribution Px given H of image suiting this description given by H, so to speak. So formally, the conditional pixel CNN models the following distribution. P of x given H is uh, of all n square pixels, P of xi given x1, x2, x up to xi minus 1 given H also. So this H, what is this H? Yeah, I'm sure you're yelling in your mind. So this H can be anything. Embeddings from another network, one hot encoding of a class. For example, H tells me that this is a dog in this image, or it tells me that there is a cat in this image, or there is a car in this image. Now, given that H, that is important information for our model. So H can tell us anything that's in the image. I'll take it one step further. Okay, first of all, let's get into this equation. So this entire thing is just convolution with H and getting some information from convolution with X and getting some information from H as well in both of these gated units. So suppose we have some information about the location or certain structures in an embedding edge. That is, edge tells me that there is a dog in the top right, there is a car in the top left, there is a human in the bottom right, and there is a person giving a PPT to on YouTube in the bottom right or bottom left, whatever. So we can spatialize this. So somehow we have a network, somehow we have this function which gives us a spatial X, uh, a spatial image, spatial vector, a spatial tensor of information corresponding to edge. So the only thing that I want to stress here is instead of having matrix multiplication, we can have convolutions too in an external information given by S. And S tells me that there is a guy doing PixelCNN YouTube presentation. That's what S gives me. And this entire thing can be incorporated into this gated function. So this is what the gated unit looks like. Please keep in mind that this is not like an RNN. Here, as you know, that RNN can go up till infinite time points until an end of sentence is received. This gated unit is what the block is of our architecture thing. So there was a 7x7 convolution and block, 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 block. So this is what the block is. So a single layer in the gated pixel CNN architecture. Convolution operations are shown in green. These are convolution operations. Element-wise multiplications and additions are shown in red. Basically, of all our previously discussed material, gated things. The convolutions with WF and WG from equation 2 are combined into a single operation shown in blue, which splits the 2P feature maps into groups of P. So basically what we're doing is instead of a convolution generating P feature maps, we're going to generate 2P feature maps, split them into two, do a sigmoid in one half, do a tan H in one half, and then multiply it element wise in order to have again P feature maps. And so similarly, this left hand side of this gated unit is how our image is flowing, and the right hand side is what the gates control is. You know, so yeah, the split feature maps allows us to parallelize the entire process. Residual connections are present in the horizontal stack. So it's just whatever we do instead of having take p convolutions first and do a tan H, and then take a p convolutions and do a sigmoid and then multiply. We directly generate two p convolutions, split them into half, do a tan H sigmoid on them parallelly, and then multiply them together. So this is just a optimization. So this is the results on gated pixel CNN and gated pixel RNN, pixel CNN versus pixel RNN also, because we're going to compare traditional pixel CNN, traditional pixel RNN, and gated pixel CNN, and how it compares to other previously image generating networks. But before getting into the results, I would like you to focus on this and try to understand what's going on here. Spend a few seconds on this dialog box, or spend a few seconds on this image, and I'm sure you'll appreciate it. Whatever is going on here. You can get into, you can understand, you can read if you want to get a better feeling of what the results are. So here this I think this slide is pretty self-explanatory. NLL is negative log likelihood test, and lower is better in bits per dimension. Here is condition. Yes, so this is what we spoke about when I told you about a vector H. We can condition an ImageNet, and one network itself, when given the one hot encoding of an African elephant, generates something very very different than when something like a coral reef or a lawnmower or a brown bear is given to it as an input. If you would like, I can, yeah, something. Something to look, something to appreciate, because this is very elegant to me. So this is also given some high level latent representation H. We can condition this. I mean, this is just conditional things. So PixelCNN autoencoders, because conditional PixelCNN have the capacity to model diverse image distributions. Conditional here means that H thing, that given some information about the image. It is possible to apply them as image decoders in existing neural architectures such as autoencoders. So an autoencoder consists of two parts: an encoder that takes an input image X and maps it to a usually low dimensional representation H, and a decoder that tries to construct the original image. So given H, so if we have a encoder decoder sort of architecture, if we have an encoder giving us H, we can supply that H to a pixel CNN decoder and it will give us back the image. So starting with a traditional convolution autoencoder architecture, replace the deconvolutional decoder with a conditional pixel CNN and train the complete network end to end. That's what they have tried. Since PixelCNN has proved to be a strong unconditional generative model, we would expect this change to improve the reconstruction. Okay, perhaps more interestingly, we also expect it to change the representation that the encoder will learn to extract from the data. Since so much of the low-level pixel statistics can be handled by the pixel CNN, the encoder should be able to omit these from edge and concentrate instead on more high-level abstract information. Okay, that's also interesting. Based based on the choice of the decoder, the encoder also changes its learning because now the encoder does not need to incorporate very tiny little small speck details into its edge. It can learn more high level things and the encoder can be confident that the pixel CNN will just take care of all other noisy aspects. So that was it. If you have any questions, you can put it in the comments. And I really enjoyed this paper, Pixel CNN, Pixel RNN. Although there are a few things which can be ironed out, but this is a very interesting paper. I encourage you to go and read it on your own as well. And look at this. Perhaps look at the outputs of their images too, which have not included in the PPT. But